For centuries, one of the simplest things we experience every single day, light, was actually the subject of one of the biggest scientific mysteries of all time. So let's unravel this incredible story.
At the very heart of it all was this one question. Is light made of tiny, little bullet-like particles, or is it a wave? Kind of like a ripple spreading across a pond. It sounds pretty simple, right? But the answer would take hundreds of years to figure out. And listen, this wasn't just some dusty academic squabble. We're talking about a 400-year-long scientific saga, just packed with genius, with stubbornness, and some really wild ideas that ended up shaping our entire understanding of reality.
So let's start at the very beginning, with the two giants of science who kicked off this epic debate.
In one corner, you had the legend himself, Sir Isaac Newton. He was convinced that light was made of tiny particles he called corpuscles. And, this idea made a lot of sense. Reflection, for example, worked perfectly. It was just like a ball bouncing off a wall. But, and this is a big but, his theory predicted that light would actually speed up when it entered water, which we now know is completely backward. Then, in the other corner, you had Christian Huygens. He argued that light was a wave. The problem with his theory? Well, waves need something to travel through, right? Sound needs air. Ocean waves need water. So Huygens had to invent this hypothetical, invisible substance that filled the entire universe, which he called the ether. A pretty huge assumption that, spoiler alert, was later proven to be totally wrong. Okay, so while this whole particle versus wave battle raged on, the folks in the wave camp had a very practical problem they needed to solve. I mean, think about it. A light bulb sends light out in literally every single direction. If you tried to draw that as a bunch of individual wavy lines, you'd just end up with an impossible scribble. How on earth were physicists supposed to diagram this in a way that was clean and actually useful? Well, they came up with this brilliantly elegant solution, the wavefront. See, instead of drawing a million messy rays, you just draw one single surface that connects all the points of the wave that are moving in perfect sync, like, say, all the crests of the wave. It's basically a snapshot of the wave's shape at a single moment in time. Super clever.
And what's really cool is how the shape of the light source actually determines the shape of the wavefront. A tiny point source, like a single light bulb, creates a perfect sphere of light expanding outwards. A line source, like one of those long tube lights, creates a wavefront shaped like a cylinder. And a source that's incredibly far away, like our sun, is so distant that by the time its light reaches us, the wavefront looks totally flat, like a plane.
Okay, so we've got a way to visualize the wave's shape, but how did Huygens explain how that shape actually travels forward through space? He came up with something called Huygens' principle. And the core idea is that you can think of every single point on a wavefront as its own little light source, sending out its own tiny new wave or wavelet. It's kind of like every drop of water in a ripple starts to create its own brand new ripple. So if you draw a line that just barely touches the front edge of all those new little wavelets, boom, you've just drawn the position and shape of the main wavefront a split second later. It was a genius way to explain how waves move. But even with this amazing model, the big debate wasn't over, not by a long shot. Both Newton's particles and Huygens' waves still had major, undeniable flaws. This stalemate went on for nearly 200 years, and the solution, when it finally came, didn't come from someone studying light at all. Nope, it came from a completely different field of physics. Just take a look at the timeline. Newton and Huygens put their ideas out there in the late 1600s. And then, basically crickets. For almost 2 whole centuries, science was stuck. Then, in 1865, a physicist named James Clerk Maxwell was working on something that seemed totally unrelated: electricity and magnetism. While he was working through all his equations, Maxwell decided to calculate the theoretical speed of an electromagnetic wave. He crunched the numbers, did all the math, and he came up with this value: 300 million meters per second. Now, you have to remember, by this point in history, other scientists had gotten really good at actually measuring the speed of light. And when they realized what had just happened, it was incredible. Maxwell's purely theoretical number for the speed of an electromagnetic wave was a perfect match for the measured speed of light. It just couldn't be a coincidence. No way! And right there, we have the resolution. Light is a wave, but it's a special kind. It's a self-propagating electromagnetic wave. It's made of these oscillating electric and magnetic fields that don't need any medium to travel through.
So Huygens was right about light being a wave, but he was wrong about needing that mysterious ether. The 200-year-old puzzle was finally solved. But discovering light's true nature wasn't just about solving some old question. It also revealed a hidden property of light that has huge technological implications. I'm talking about polarization. You see, the light that comes from the sun or a light bulb is unpolarized. That just means its electric field is vibrating randomly in all directions, up, down, left, right, diagonally, you name it. Think of it like shaking a rope just wildly and chaotically. Polarized light, on the other hand, is much more orderly. Its electric field vibrates in only one specific direction, like shaking that same rope in a nice, clean, controlled up and down motion. So, how do you get polarized light? Well, the simplest way to picture it is with an analogy. Imagine you're shaking that rope all over the place, and you try to send the wave through a picket fence with vertical slats. The only part of the wave that can actually get through is the up and down, vertical motion. All the side-to-side and diagonal wiggles just get blocked by the fence posts. So the wave that comes out on the other side is now vertically polarized. And this is precisely how a Polaroid filter works. It has all these long-chain molecules all lined up in the same direction, creating a sort of molecular picket fence. It only allows light waves that are vibrating parallel to those molecules to pass right through, blocking everything else. This one simple principle is the basis for so much of our modern tech. Polarized sunglasses? They block the horizontally polarized light that reflects off roads and water, which is what cuts down on glare. 3D movie glasses use two different polarizations to send a separate image to each of your eyes, creating that illusion of depth. And yeah, every single LCD screen, from your phone to your TV, relies completely on polarization to work. So when you trace it all the way back, you realize this massive, centuries-long debate over particles and waves, it wasn't just some academic exercise. Solving it revealed a fundamental property of our universe that we now manipulate every single day to create the technology that defines our world. It really makes you wonder, doesn't it? From the screen you're watching this on to the very nature of light itself, it's all governed by the physics of waves. What other hidden rules are out there, shaping our reality, just waiting to be discovered?